Good morning, everyone. My name is Jia Qing from the University of Maryland, and today I'm excited to present our work, the hack equivalence verification checking for the code transformation via equality saturation. It's a joint work from the University of Maryland with the Pacific Northwest National Lab. Compilers today perform source-to-source transformation like the loop tiling, loop unrolling, and the Boolean and the arithmetic rewrites to improve the performance. But here is the key point. Where we optimize for the speed and the efficiency, we never stop to formally verify if the transformed code is still semantically equivalent to the original code. Imagine a chain of the optimization including the loop unrolling, loop tiling, loop hoisting, and somewhere along the optimization chain, a bug may generate it. Without a formal check of this code, we may not even notice of the generated bugs. Let's consider a simple MIR loop. It does a bitwise NAND on the two arrays. Now we perform three different optimizations, including the loop hoisting. It will move the true constant inside the loop, and the De Morgan's law. It replaces the A NAND B with the not A or not B, and the loop tiling is turning a flat loop into a nested one. Individually, this optimization looks innocent. Together, they completely alter the structure while intending to preserve the behavior. But can we prove they are equivalent to the original code? Unfortunately, most existing tools fall short. Polycheck focuses on the affine control loop, control flow transformations, and the other SMT-based tools handle the data path logic. But none of them can handle both of the data path and the control flow transformation in a unified manner, especially for the MIR-based optimization. This reminds me of the eGraph. It is a data structure that can compactly represent a set of the equivalent expressions. They allow us to explore all possible rewrites in a program and capture the semantic equivalence by merging equivalent form into a single class. In eGraphs, our job becomes, can we show that the original and the transformed version of the program can collapse into a same equivalence class? We propose Hack. It is a hybrid equivalence checker built on the eGraph and designed for MIR code. Hack uses both of the static rewriting rules for the data path transformation and the dynamic rule generation for the runtime-dependent control flow changes. It takes the MIR code as input and translates it into an internal graph representation and then use the equality saturation to check their equivalence. We build a custom graph representation for the MIR that mimics the AST like the structures. The graph nodes are the MIR operation and the graph edges represent the data flows and the variable paddings. For the loop structure, we extract the loop boundary, the loop steps, and isolate the block bodies to preserve the data dependence and the evaluation order. The structured representation allows Hack to automatically verify variants like the loop hoisting even before applying rewrites. Let's talk about the data path transformation. The data path rewrites are handled through over 60 predefined rules, including the Boolean laws like the De Morgan's law and the double negation, and the arithmetic laws like the associativity and the shifts as it multiplies. For example, in our earlier motivating example, we perform De Morgan's laws in the original code. We represent not A as A XOR true, and the NAND AB as not A or not B. This allows both variants to merge into the same E-class to prove their equivalence. The other part of the rewriting is the dynamic rewriting for the control flow transformation. Now, here is the challenge. Control flow transformations like the loop unrolling or tiling often dependent on the runtime parameter, like the tiling factor, the loop boundary, the unrolling factor, or other dynamically generated variable. The static rewriting cannot handle the control flow transformation. So Hack introduced a dynamic rule generator. Specifically, we first identify the control flow patterns, and then we verify the transformation condition using Z3 SMT solver. Finally, we inject the according rewriting rules at runtime. Let's recap the motivating example for the loop tiling. We start with a simple loop. It is a baseline from the left of this page and transform it into a partially tiling version. It is the right figure in this page. Hack dynamically construct the matching pattern and verify the control conditions via Z3 SMT solver and create a custom rewrite rules. The dynamic rewriting rules is shown in this page. Now let's talk about the heart of the hack. It is the eGraph runner. The input is the graph representation of your MIR program, and it takes the hybrid rule set. It contains all of our static data path rules, plus any of the dynamic rules generated for the control flow transformation. First, we apply all of the static rewrites and perform one round of saturation and check if the root nodes of the two programs have merged. If yes, we are done. If not equivalent, we scan the current eGraph for the control flow candidate. For example, the loop that matches the unrolling, tiling, and the fusion patterns. And we inject the corresponding dynamic rules. The loop is well repeated until either we prove equivalence of the input code or no new equivalence rules can be generated. The designs elegantly unify both of the data path and the control flow check in one engine. For more details about the technical part of the eGraph runner, please read our paper. Next, we will clarify our formal stance. Hack is sound but not complete. It means the hack can produce, will not produce false positive. If hack says equivalent, you can trust it. The static rules come from proven algebra or Boolean rules, and the dynamic rules are SMT check. Hack has the possibility of the false negative. Some of the true equivalence may lie outside of our current rule set. In practice, that means hack will never incorrectly certify two inequivalent programs as equivalent, though it may conservatively report not equivalent in some edge cases. Now we evaluated hack on a suite of the standard kernel from Polybench C and the Polybench NM benchmark. It contains across 13 benchmarks, including the Gem, the Lu, the CN Forward, the Jacobi, and more. We successfully verify every transformations. We will verify for both of the control flow and the data path transformation and illustrate the bug we identified. Now let's examine our nested unrolling control flow experiments. On the x-axis, each point is labeled unroll K and the unroll K. It means we first unroll by a factor k, and then unroll the results again by the same factor k for the k from 2 to 16. The left chart plots the resulting number of the E-class of the E-graph. The right chart shows the end-to-end verification runtime in seconds. You will notice for both of the E-class counts and the runtime scales roughly quadratically as k increases. This matches the quadratic code growth for the nested unrolling. Despite that, the simpler tiling and the single unrolling finish under 1 minute. For more experimental results for the control flow transformation, please read our paper. For the data path transformation, we generated the benchmark ranging from the 15 to 108,000 lines of code, focusing on the Boolean and the arithmetic rewrites. The runtime and the number of the E nodes both scale linearly with the code size. Even at the 108,000 lines of code, Hack finished under 40 minutes, dominated by the static saturation. This predictable scaling demonstrated that the equality saturation remains feasible for large code bases. Beyond the verification, Hack uncovers some of the real bugs in MIR affine optimization. Here we illustrate a typical bug. It is the read after write hazard. Loop fusion reorders the memory access, corrupting the data dependence. The source and the fused code is shown in the left and the right figure. After fuse the code producing the non-equivalent output with the original version. Such read after write hazard can silently corrupt the results. That concludes the technical part of the hack. We have shown a unified approach for both of the static and the control flow equivalence checking in MIR. Hack is sound and scalable to the real-world benchmark. Thank you for your attention. Happy to take any questions.